12.1 Estimating Limits Graphically. Calculus centers around two fundamental problems: finding the equation of a line tangent to the graph of a function at a point, and finding the area between the graph of a function and the x-axis. Fundamental to the solutions of each of these problems is an understanding of the concept of a limit. Recall from lesson 1.3 that if f of x approaches a unique value L as x approaches c from either side, then the limit of f of x as x approaches c is L, written limit as x approaches c of f of x equals L. A function can have a limit without having a function value. So if this function was approaching a y value of, let's say, 3, but at this function value right here, there isn't one, the limit would still be 3. You can apply this description to estimate the limit of a function f of x as x approaches a value c, or limit as x approaches c of f of x by using a graph or making a table of values. Example 1. Estimate a limit. Estimate limit as x approaches 2 of negative 3x plus 1 using a graph. Support your conjecture using a table of values. This is a line with a y-intercept of 1, so we have a y-intercept of 1, and a slope of negative 3. So we can go down 1, 2, 3, and right 1. 1, 2, 3, and right 1. And here is the line. And we find out that as x approaches 2, as x approaches a value of 2, y is approaching a value of 1, 2, 3, 4, 5. Negative 5. Now we can support that by plugging in values into the function. For example, 1.9 is negative 4.7. 1.99 is negative 4.97. You can see as x approaches 2, y is approaching negative 5 from either direction. So when you plug in 2.1, you get negative 5.3. So the function is approaching negative 5 on the right-hand side as well. Let's go to the calculator and see how we can enter some values rather easily. Let's go to y equals, and we'll enter negative 3x plus 1. And if you go to table set, instead of the calculator autoing the values, we can have the calculator ask for the values. Now when we go to table, everything's blank, but we can enter 1.9, and we see that it's negative 4.7. 1.99 is negative 4.97, and 1.999 is for a negative 4.997. It's just a nice handy way to fill in these tables rather quickly using the calculator. Estimate a limit that does not equal f of c. Estimate the limit as x approaches 3 of x squared minus 9 over x minus 3 using a graph. Support your conjecture using a table of values. Well, now we can go to y equals. Let's clear this. Let's have x squared minus 9. X squared minus 9. 9. Let's try that again. There we go. Divided by x minus 3. So we have x minus 3 in the denominator. And when we graph this, let's hit graph. Yeah, bad window. Let's go window and number 6. Whoops, let's go zoom number 6. And we see that this is a line, but we are approaching a value of 3. So let's try to plug in 3. Let's go table, let's go 3, and you're going to get an error because we got to remember how we graph our rational functions. We have x plus 3, x minus 3 on top over x minus 3. Well, these cancel, and we're left with a line, but a hole in the graph at 3. So at 3 plus 3 at 3, 6. So this has a y-intercept of 3 and a slope of 1. So here's the line right there. Here's the graph. But we have a hole at 1, 2, 3, 1, 2, 3, 4, 5, 6. There's a hole there. Well, we can plug in values, and we can notice that we're approaching 6 from either side, even though at 3 we do not have a function value. We actually have a limit. The limit is 3. Oh, excuse me. We're approaching 3. The limit is 6, I mean. Independence of limit from function value at a point. The limit of a function f of x as x approaches c does not depend on the value of the function at point c. We can have a limit without having an actual function value or an actual point there. So this function has a limit because the right and the left-handed limit equal each other, so there's a limit at c. This one also has a limit that is L. L's the limit, even though the function value is n. This one has a limit, and the function value is exactly the same. So the limit and the function value are both L, and that's the definition of continuity at a point. It is continuous at C because the limit and the function values are equal. In finding limits using a table or a graph, we have looked at the value of f of x as x approaches c from each side. We can describe the behavior of a graph from left and right of x more concisely in terms of one-sided limits. If the value of f of x approaches a unique number L as x approaches c from left, then we write limit as x approaches c from the left. That minus sign means from the left of f of x equals L. Now if we have a plus sign right there, that means it's asking for the right-hand limit. The limit of a function f of x as x approaches c exists if and only if both one-side limits exist and are equal. That is, if the left-handed limit equals the right-handed limit, then we have a limit at c, at that x value. Estimate each one-sided or two-sided limit if it exists. So let's look at the left-handed limit of this function right here. Now, to the left of 0 is negative numbers. Now, not only are we to the left of 0, but we're left, but really, really close to 0, like infinitely close. So what would we get if we plugged in negative 0.0001? That's really close to 0, but on the left-handed side, all the x's would be 0.0001. Now on the top, when we take the absolute value, we'd get 2 times negative 0.0001 over negative 0.0001. Well, that'd be positive, not negative anymore. That'd be positive. These would cancel, but it would leave a negative 2. The left-handed limit is equal to negative 2. Now, what about the right-handed limit? 0.0001 over 0.0001. Well, when we take the absolute value of this, it's still positive. Those would cancel out, and the right-handed limit would be 2. So the limit at 0 does not exist. These are not the same value. Let's find the left hand, right hand, and limit at 1 for this piecewise function. Let's make a little sketch. If we plug 1 in here, we get 1 to the third plus 2, that's 3. So we have the point 1, 3, but it's not equal to, so that's going to be an open dot. So 1, 3 is an open dot, and then to the left of 1, we have the x to the third function. Now to the right of 1 and at 1, we have 2 times 1 is 1, 1 plus, or 2 plus 1 is 3. So we have 1, 3 also, but this is now a solid dot, and it's a line with a slope of 2. Now the left-handed limit is 3. The y value is approaching 3, so this is 3. The right-hand limit is 3 also, so the limit at 1 is 3. Estimate each limit if it exists. Let's go to the calculator for these. Let's clear, and we have 1 divided by x minus 4 squared. So we need squared here. Let's graph this, and what we see is at 4 there's a vertical asymptote, which means that the function is shooting to infinity on both right and left side of 4. But that doesn't mean the limit's infinity. The limit does not exist. Now the same thing will happen for 1 over x at 0. So we take 1 divided by x, we delete the rest of this, and when we graph, we see we have the graph is shooting down to negative infinity on the left side and shooting up to positive infinity on the right side. So at 0, the limit does not exist for this one as well. The graph of f of x equals cosine of 1 over x suggests that as x gets closer to 0, the corresponding function values oscillate between negative 1 and 1. And what's interesting about this is the graph never really gets to 0, but it oscillates forever and ever and ever and ever, just stacks up getting closer to 0. So there's no limit at 0, but it's because of oscillation. It oscillates infinitely to 0 and never gets there. Now on 5a, the exact same thing happens. Let's take a look. We have a limit of sine of 1 over x. Sine of 1 divided by x. Now, x can't be 0 because that'll put 0 in the denominator, but the graph is one of oscillation. Now, we can't see it very well there because we need to change the y values. So we have window. We have, let's go from negative 1 to 1 on the y values, and now take a peek at it. And we see we have this oscillation. Now, going from negative 10 to 10, that's not a great window either. How about if we go negative 1 to 1 for everything? And we see that infinite oscillation a lot clearer. If we go from 0.1 to 0.1 on the x, we'll still see that oscillation. So the limit does not exist. Now what about x squared sine of x? We have x squared and then times the sine of x. And for this one, we notice that the graph just passes right through the point 0, 0 without any problems whatsoever. So the limit is actually 0. Summary: how can the limit of f of x as x approaches c does not exist if f of x approaches a different value from left and from right? So the left and the right hand limits, they're not equal. Then we don't have a limit at a value. What if on the left it goes to infinity, on the right it goes to negative infinity without bound? Then we wouldn't have a limit at the value. And the third way you could possibly not have a limit at a value is with this oscillation. Estimate each limit if it exists. What if we're going limit as x approaches infinity this time of 1 over x? Let's clear this. We're going to do 1 divided by x. And let's go zoom 6, and we see with 1 over x, as x approaches infinity, as x gets really, really big, this function is leveling off to 0, so the limit is 0. What about letter B here? Let's go y equals, we have negative 3 divided by x squared, and then we'll add 2. And when we graph this, we notice that as x gets really, really negative, this graph is leveling off to a value, and it actually levels off to 2 because as this denominator gets really big, this piece will be 0, and the limit of a constant is just that constant, so the answer is 2. Let's look at the last function. It's a really interesting one in my opinion because it does two different things on each side. We have e to the x and then sine, there it is, of 3 pi x. And when we graph this one, here we go, we'll wait a little bit. To the right, this is going infinitely up and down. It's just getting bigger and bigger and bigger and bigger. So this one on the right side, as x approaches positive infinity, that limit does not exist. But on the left, we notice if we went from right to left, it's getting smaller and smaller and smaller and smaller. So on the left side, this one's actually approaching 0.